Let's just review logistic growth, because we had that in pre-cal. You remember logistic growth? We don't abbreviate logistic LOG, right? Because we read that as log. This is the soft G sound, right? Logistic. Logistic growth, if you recall, started off growing exponentially. But at some point, it could not continue to grow at an increasing rate because there was a limit to its growth. And so it continued to grow, but at a decreasing rate. And so it had this nice S-curve. Much like exponential, though, it has to have a seeding value, a starting value. That's the y-intercept. There is a horizontal asymptote down there on the x-axis, and this limit to growth was y equal to L. This point in the middle was pretty significant because it is, first of all, the inflection point, where the graph, in this case, changes from concave up to concave down. But what that means is that's where the derivative is at an absolute maximum. That's where the slope of the tangent line is the steepest. So that would be where the thing that's growing logistically is growing at the fastest rate. And do y'all remember the y value at which that occurred? It's always half of the limit to growth, right? So I think we had like a rumor spreading around a campus of 2,000 students. The rumor is going to be spreading the fastest when 1,000 students have heard, right? Or Wasselfest, I think y'all had the Wasselfest question where the Grinch is going to shut down Wasselfest. Right. If 10,000 people attended Wasselfest, then the Wassel spirit was growing at the fastest rate when 5,000 people had caught the Wassel spirit, so on and so forth. So if we kind of try to quantify this, remember what makes a purely exponential function exponential. The rate of change of the y value with respect to time was directly proportional to what? Remember the sect equation? It was directly proportional to y itself. So the bigger y is, the bigger the rate of change, and the faster the rate of change, the more y you're going to get. And they were directly proportional to k. But for logistic, it can't continue to grow unchecked like that. So what we could do is modify the pure exponential model. We can say the rate of change of the y values now with respect to time, they're still going to be directly proportional to the current amount. Okay, and that would be, let's show that in brown right here. This would be like the current amount right here. But it's also going to be proportional jointly to the difference between the current amount and the limit to growth, which would be L minus Y. So if you're putting it back in the context of a rumor spreading on campus, the rumor is growing around campus at a rate that is jointly proportional to both the number of students who have heard the rumor and the number of students who haven't heard the rumor, okay? That's how we can quantify it. And so this is how we could write it in a mathematical sentence. So dy dt is not just equal to k times y. That would be purely exponential. And if that's the case, what is the general solution to the purely exponential equation? I already said it. Y equals the sect equation, right? CE to the KT. What we're going to do in this section is we're going to develop the general solution for the logistic scenario, which is dy dt equals ky times L minus y, where L is your limit to growth. And once we develop its general solution, you're going to memorize it like y'all memorized y equals sec being the general solution to k times y. Y'all did memorize that, right? Y'all are a little slow to respond, but y'all are just being, you didn't want to hog the microphone. Good. Okay, so there you go, blah, 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 blah. Here it is. Now, in order to solve this differential equation, let's go ahead and start and see how far we can get. If I wanted to solve that differential equation, I would have to separate the variables, right? Which means y's, dy's on one side, and t's, dt's, and constants possibly on the right side. Well, k is a constant. So if I separate the variables, I'm going to multiply both sides by dt. And I guess since I have a factor of y and a factor of L minus y, those are going to have to make it to the other side. So 1 over y times L minus y, and that would equal k times dt. That ought to separate the variables, and then I'm going to integrate both sides. What would be the antiderivative on the right-hand side? What's the antiderivative of a constant with respect to t? T, right? T times K, or KT, plus C. But what's the antiderivative on the left side? Do we know how to find the antiderivative of that? Let's look at it from a different perspective. Let's say I ask you to find the antiderivative of 1 over x times 4 minus x with respect to x. Because that's essentially what we have. Is that something we know how to find the antiderivative of? Well, as it is, we don't, because this is your inside function. This derivative is not 1 over x. If you expand it, you get 4x minus x squared. You're going to notice that if you complete the square, it's not going to work. It's not going to be an arctangent because you're going to have a negative coefficient of your x squared. Long division, no, that doesn't work. By parts, you're going to see that that doesn't work. So guess what? We currently do not have a way to do that. So right now, we cannot solve the general solution for logistic. It's going to require a new technique. Guess what the technique is going to be called? Integration by partial fractions. By the something, 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 heavy something. Yeah. All right. So before we learn that method, let's look at example 1. Let's take a trip down memory lane and pretend like we're back in maybe late Algebra 1, early Algebra 2. We want to add and then simplify these two terms by finding a common denominator. Ooh, it even tells us how to combine them. What do we need in order to combine two fractions? A common denominator. Darn it, it said that. I was going to ask you all that. All right, so what is the LCD, the least common denominator, or the LCM of your denominators? 2x minus 1 and x minus 3. Their product. Very good. So, to do it the right way, instead of the crisscross applesauce method, we're going to need to multiply this one by x minus 3 over x minus 3, which is equivalent to what? 1, and you can multiply an expression by 1. Minus 2 over x minus 3, we're going to have to multiply that one by what it's lacking, which is the 2x minus 1, bless you, over the 2x minus 1, bless you. All right, so now we know that the common denominator is 2x minus 1 over x minus 3. So we can build a shelf and put them in the bottom. And if I distribute, I get 5x minus 3. And if I distribute the negative 2, I get negative 4x plus 2 minus 15. Thank you. 15. Thank you. You would get that. And if I simplify that, I get 1x minus 13. Is that right, Brandon? I've lost my confidence. I think that's right. X minus 13, all over 2x minus 1 times x minus 3. Yeah. Now, if we want, we could expand the bottom as well. That would give us 2x squared. The inside's going to give us negative x. The outside gives us negative 6x, so that would be a negative 7x. And then plus 3, sorry. There we go. So that's another version of it. Okay, sweet. Any questions on that? Seems kind of random. Maybe I can give you one like that on the test. Maybe. Maybe free response. Show all steps. All right, check, 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 check. All right. Example 2. Example 2. We want to evaluate the integral of x minus 13 over 2x squared minus 7x plus 3. All righty. You're walking up to this problem and you're like, what's up, problem? The inside function very well could be the denominator, right? What's the derivative of 2x squared minus 7x plus 3? 4x minus 7. Now, is 4x minus 7 or a multiple of it in the numerator? That is, are we only off by a constant multiple? No. If I factor it out of 4 to make the first term look the same, I get 7/4, which is not 13. So the derivative of that inside function is not the top. So that's not going to work. It's not going to be a natural log rule. Darn it. What else could I do? Long division. Is that a good candidate for long division? No, because that only works when the degree of the numerator is what compared to the bottom? Larger or equal to. And we have one that's already smaller, so that's no good. What to do, what to do, what to do. Could I put x over each, or over the entire denominator, and 13 over the entire denominator? In other words, could I say it's x over all of that blob, and then minus 13 over all of that blob? I could. I really could, but will that help me? No. No, it will not. I'm stuck. By parts? It's in this section, so no. No, by parts is not necessarily going to work. By parts and fractions. Okay. James, I heard you say when we went to this problem that looks familiar. Where have you seen that before, the integrand? The problem before? Hey, what do you know? You have a very good short-term memory. I'd forgotten about it already. Yeah, here it is.
Pardon the interruption, teachers. Please turn your TVs to channel 4 for the morning announcement.
I don't think so.
View them on your iPads at bhstv.com.
All right, so the integrand is equal to this, which means the integrand is equal to that, which means the integrand is equal to that, which means the integrand is equal to the green line, which means the integrand is equal to that. Let's rewrite it like that. What do you say we rewrite it like that? 5 over 2x minus 1 minus 2 over x minus 3. Write it where you can see it, and then cut and paste it. All right. You just got to do that every time. All right, so if I do that, that might make it a little bit easier, right? Because now, in each term, I have an inside function that's linear, which means its derivative is going to be a constant, which is what I have in the top. It's going to be a natural log rule each time with maybe a correction, yes? So let's see, in the first term, the 5 goes along for the ride. The derivative of 2x minus 1, oh, getting excited. What's the derivative of 2x minus 1? 2, so we have a correction of 1/2. And because our inside function's in the bottom to the first, it's going to be a natural log of absolute value of the blob. Good. There's the first term. Minus 2 in the next term goes along for the ride. What's the derivative of x minus 3? 1. So we have a correction of 1/1, or nothing. And it's the natural log of what, Nick?
The absolute value.
Absolutely. The absolute value of x minus 3. And we're done, right? Plus c. Good. Sweet. So, of course, you can simplify and call that 5/2. You know, College Board might bring that up and make it squared, in which case you would need the absolute values, but that's not the point of this lesson. The point of this lesson is to realize that if I could somehow rewrite this to look like that, it's going to make the problem easier. Now, the only reason that it worked this time is because I gave you this problem first, which at the time seemed kind of weird and out of place, but now you know why I gave it to you. Am I always going to give you a problem like this prior to having you do a problem like that? No, no. So what this section is about, partially, is to figure out how we can do that on our own. And we're going to do it by a method called partial fraction decomposition. Okay? We're going to look at a version of partial fraction decomposition. So here is a mathematician by the name of Oliver Heaviside. Heaviside. Heaviscid. And notice he was actually a pretty thin man and parted his hair down the middle. S-I-D-E. Sorry, S-I-D-E. Notice also he had facial hair. Lucky. Anyway. Yeah. We're going to do a version of partial fraction decomposition that is very simple to do using a method or kind of a rule of thumb that Mr. Heaviside kind of gets credit for discovering. And he's going to be watching us the whole time with his hands in his pocket. So let's look at a problem like this, example 3. Have we worked a problem prior to example 3 that gave us a solution that is the integrand here in example 3? No. So we're kind of left to our own devices. Step one, though, is walk up to the problem and see if that's not the inside function. What's the derivative of x squared plus x minus 2? 2x plus 1. Is that what we have on the top? Are we off by just a constant? No. But what if we had a 2x plus 1 in the top and it was x squared plus x minus 2 in the bottom? Then it would just be a what rule? Natural log. We'd be done. What if there were not a 2x plus 1 in the top but a 4x plus 2 in the top? Would it still be a natural log rule? Yeah, we would factor a 2 out of the top, bring it out front, and we'd have it. So when you have a quadratic in the bottom and a linear in the top, it could be a natural log rule. But in this case, it's not. So here's how you're going to do partial fraction decomposition by the Oliver Heaviside cover-up method. Step one, if it's not already done, factor the denominator. Factor the denominator. All right, so that's going to be x plus 2, x minus 1. Now notice it factors into the product of two non-repeating, bless you, linear factors. Non-repeating means that both of their exponents are to the first power. If one of them was squared or one of them was cubed, that would be a repeating factor. It would have multiplicity greater than 1. And notice they're both linear, they're both x to the first. The Heaviside cover-up method only works for non-repeating linear factors, which is what the BC exam is going to expect you all to do. There are more sophisticated decomposition methods. All right, so here's how you do the Heaviside method for partial fraction decomposition. You are going to create two terms. You are going to decompose the fraction into its two partial fractions, and that's why it's called partial fraction decomposition. One of the terms is going to be x plus 2, and one of them is going to be x minus 1. As you saw before, we got the common denominator by multiplying the two denominators that we had, so we're kind of working backwards. Now here's how the method works. Once it's factored in the denominator, all we're looking for now is the two new numerators of our two partial fractions. And the easiest way to find them by the Oliver Heaviside cover-up method is this. Pick one of the two factors up above in green. I'll take the first factor. What value of x, when you plug it into x plus 2, gives you a 0? Negative 2. Keep that negative 2 in your mind, and now cover up the x plus 2 factor. This is why it's called the cover-up method. Now plug a negative 2 into every x that's left, including the numerator and denominator. What do you get when you plug a negative 2 into the top? You get 3, and when you plug a negative 2 in the bottom, you get negative 3. What's 3 divided by negative 3? Negative 1. Guess what? That negative 1 becomes the new numerator down below in the term whose factor you covered up. Yeah, it's easy. Thank you, Oliver Heaviside. And we do the same thing for the second one. What x value makes x minus 1 0? 1. Cover it up. Plug into 1 to what's left, and you get 6 over 3, which is 2. Positive 2 becomes the new numerator for the second term, whose denominator is the factor you covered up in the line above. And that's it. If you want to check very quickly off to the side, because you don't believe it works, do your crisscross applesauce method, which is a quicker way to do it. Negative 1 times x minus 1 gives you negative x plus 1, plus, multiply the other way, you get 2x plus 4, all over their product, x plus 2 times x minus 1. And what do you get in the top? You get an x plus 5, which is, yeah, it works. It works. So once you get to this step here, it's a piece of cake. You should have two linear factors in the bottom because we're only doing this for linear factors, which means the integration is probably going to be what each time? A natural log. You just want to make sure that the derivative of the inside function is not going to generate a correction. So in this case, it doesn't. So you have negative natural log of the absolute value of x plus 2, and you're going to have plus 2, the natural log of the absolute value of x minus 1. And then, of course, plus c. And you're done. Now, remember that if this term had been 1 minus x instead of x minus 1, you would have a correction of a negative 1. That's it. It's that easy. Piece of cake. Oliver Heaviside. Okay, so when does this method work? This method works when you have a ratio, a rational function, and your denominator factors into the product of non-repeating linear factors. Okay? Non-repeating linear factors. We have time for another? Oh, maybe so, maybe not. Let's try and, well, let me just make this note. I don't think we're going to have time to do it. If you notice up here, the degree of the numerator in relation to the degree of the denominator, it was smaller, right? We said if the degree of the top was greater than or equal to the degree of the bottom, what strategy that we've already talked about might we have used? Long division. That's still going to be a priority because the Heaviside decomposition method only works when the degree of the numerator is smaller than the degree of the denominator. So we'll pick up with example 4 tomorrow, and if you notice, the numerator is degree 4 and the denominator is degree 2. So you can't jump straight to the Heaviside decomposition method. You would have to first do long division, and then as a subsequent part down the road inside that problem, maybe the decomposition method works. Okay, now the decomposition method, where are we going with all this? Why are we looking at this method now? Remember, our goal was to find the antiderivative of 1 over y times L minus y with respect to y. Guess what method we're going to use to find its integral? The partial fraction decomposition by the Oliver Heaviside cover-up method. Heaviside, H-E-A-V-I-S-I-D-E. I'm out of here. There we go.